Welcome everyone, and thank you for joining the webinar today on noise and artifact searches in EEG, how to identify, reduce, and avoid. My name is Francesco Mucci, and I am the EEG LTM ICU Clinical Application Specialist at Natus Medical for EMEA region. I will be hosting the session and I will be your speaker and presenter today. Before to start the presentation, I would like to provide you with some general and important webinar information. Natus Neurology Training Academy is a platform that is focused on educational programs to better support customers in the use and optimization of Natus products. And our mission is to provide the participants with the technical, application, and clinical knowledge and expertise to improve patient testing and care. In addition to the invitation for the webinar, you should have received the webinar calendar for the current year with all scheduled webinars. So if you didn't get the calendar, please ask your regional manager for a copy of it, or go directly to visit the Neurology Training Academy website, where you can find all the upcoming webinars. I would like to take the opportunity to inform you that Natus Neurology Training Academy also arranges extra and advanced service and system operation training courses in Munich and Dubai. You can find also all the information related to the trainings in the website, or please ask your regional manager in order to get more information and receive the training calendar. And so, trying to join us at the next trainings. Another strong point of Natus Neurology Training Academy is represented by specialized people who belong to the clinical application specialist team and who provides customers and clinical and technical support in each modality, with EEG, EMG, and SV. And all Natus products and solutions we develop. Our team of experts includes physicians, technicians, engineers, and other skilled professionals with years of field experience in a wide range of lab diagnostics modalities. About me, I am a biomedical engineer and I graduated at the University of Florence in Italy, and I did the internship at Delft University of Technology in the Netherlands. I worked for an important Italian company for 5 years, and I have joined at Natus Medical for almost 1 year. The purpose of this webinar today is to discuss the main sources of artifacts in EEG in order to provide you the basic information and the knowledge for identifying the main artifacts in the EEG recordings, or simply for letting you know the artifacts can occur in different ways and arise from several sources, and so you will be able to take into consideration specific precautions in order to avoid the possible artifacts contaminating the EEG. In addition, some simple solutions and heat will be provided in order to reduce or remove, where it's possible, the effects of artifacts. So, with the first slide, we will have a brief introduction and definition of artifacts in EEG. Then, in the main part of this presentation, I will discuss the different types of artifacts in EEG and possible solutions for minimizing their effect. At the end of the webinar, we will have some slides where I will show some methods for avoiding to introduce artifacts into the EEG and obtaining good recordings. Let's start with a brief introduction of artifacts and noise in EEG. As you know, electroencephalography is one of the key tools for observing brain activity, and it's the key to diagnosis of many neurological disorders. EEG is widely used in many areas of clinical work and research. It's a readily available test that provides evidence of how the brain functions over time. The different activity is described by amplitude, frequency, location, for example, frontal, temporal, parietal, and occipital lobe, symmetry, and reactivity. And each of these characteristics has a great importance in the interpretation of the EEG activity. Mainly, artifacts and noise contaminate amplitude and frequency in EEG. EEG has a frequency content ranging from 0.01 to around 100 Hz and varies from a few microvolts to approximately 100 microvolts. But the amplitude may be well above, especially when corrupted by non-cerebral activity. A typical adult human EEG signal is about 10 microvolts to 100 microvolts in amplitude when measured from the scalp, and is about 1 to 2 millivolts when measured from subdural electrodes. EEG or the ground reads are classified into 5 different frequency bands. Delta band about 0.54 Hz, theta band 4-7 Hz, alpha band 8-12 Hz, beta band 12-30 Hz, and gamma band greater than 30 Hz but typically less than 100 Hz. One of the biggest challenges in using EEG is the very small signal-to-noise ratio of the brain signals that we are trying to observe, coupled by the wide variety of noise sources. Artifacts and noise in EEG is some electrical activities arising from sources other than the brain that are able to modify, distort, or cancel the brain activity. Sometimes artifacts that occur during the recording are very clear, and so we are able to distinguish them from the background EEG activity, avoiding to take them into consideration and interpreting properly the EEG activity. Many other times, unfortunately, artifacts appear very similar to the EEG signal, and they could simulate some abnormal EEG activities, so they could lead the doctors to interpret the EEG wrongly. For this reason, the identification and the removal of artifacts and noise are two big issues and challenges in EEG, both for technicians who register the EEG signal and doctors who interpret the brain activity. We can group artifacts in two main families: physiological artifacts and non-physiological artifacts. In the first group, we can find all the artifacts generated and coming from different parts of our body, and we can distinguish artifacts related to ocular movement, cardiac activity, muscle activity, electrodermal activity, and movements. Whereas in the second group, we find all the artifacts that arise from outside the body, and we will see artifacts generated by electrodes, electrical interference, and external devices. Let's start with the physiological artifacts. In particular, in the next few slides, we will focus on the ocular movements. Ocular artifacts are maybe the most common artifacts that we can observe during a routine EEG, and generally they are very easy to identify. Typically, the ocular movements can be observed in the frontal region, but it's also common to detect them in the anterior temporal region, and the activity is synchronous and symmetric on both sides. The eyeball acts as a ball with a positive pole oriented anteriorly, the cornea, and a negative pole oriented posteriorly, the retina. Under normal conditions, the potential difference between cornea and retina is about 100 millivolts. When the globe rotates about its axis, it generates a large amplitude alternate current field, which is detectable by an electrode near the eye. The other source of artifacts come from EMG potential from muscles in and around the orbit. When the eyes don't move, a stable potential is generated, and it's not recorded by the conventional EEG amplifiers. But when the patient moves the eyes, The relative activity generates a different potential that can be recorded by the nearest electrodes. During EEG recording, different types of ocular artifacts can occur according to the ocular movement. We can distinguish blink artifacts, eye flutter artifacts, slow roving eye movement, lateral eye movement, lateral rectus spike. The most common artifact related to the ocular movement and which can be observed during a clinical EEG is the blink artifact, as it displayed in this picture. Vertical eye movements typically are observed with blinks and is called belt phenomenon because the artifact has a typical bell-like shape. The blinker causes the positive pole, that is the cornea, to move closer to frontal electrodes FP1 and FP2, producing a symmetric downward deflection. During the downward eye movement, the positive pole of the globe moves away from frontal electrodes, producing an upward deflection best recorded in channel 1 and find the bipolar longitudinal montage. So FP2, F8 and F1, F7 in the picture. Eyelid movements with its myogenic potentials also may contribute to ocular artifacts with eye opening and closing. Repetitive blinks usually appear as a sequence of the slow wave ocular artifacts and thus resemble rhythmic delta activity, as shown in the picture with the red selection. Although ocular flutter involves vertical eye movements, it differs from repetitive blinks by being more rapid and having lower amplitude. Because of this, its EEG artifact is more rhythmic and lower amplitude, which gives it a greater resemblance to rhythmic delta activity. Ocular artifact from lateral gaze is most apparent during drowsiness, when the eyes demonstrate repeated slow lateral movements. This produces rhythmic, slow artifact anteriorly with a field that is maximum at the frontal poles and temples and a frequency that is less than 1 Hz. Because the amplitude is also low, the wave also resembles an unstable baseline for the superimposed EEG activity. The most characteristic feature of the low amplitude slowing due to roving eye movement is the opposite polarity of the slowing in the left and right frontotemporal regions. The artifact typically occurs intermittently and is accompanied by slowing of the alpha rate. Lateral eye movement most affect the lateral frontal electrodes F7 and F8, as the red arrows show in the picture. During the left lateral eye movement, the positive pole of the globe moves toward F7 and away from F8. Using a bipolar longitudinal montage, maximum positivity in electrode F7 and maximum negativity in electrode F8 is recorded. With the right lateral eye movement, the opposite occurs. The so-called rectus laterals may be present in electrode F7. It's observed best in the vertex reference montage. The EEG during more rapid lateral eye movements sometimes includes a single move from a contraction of the lateral rectus muscle. In the picture on the right, a representation of the muscle which generates this type of artifact. This low amplitude transient is termed a lateral rectus spike and usually is present at the F7 during a left lateral eye movement or F8 electrode during the right lateral eye movement. The lateral rectus spike may be followed immediately by the lower eye movement artifact in the same location, and this may result in what appears as one wave with a morphology that resembles the focal interictal epileptiform discharge. In order to avoid to generate the ocular artifact, we should ask the patient to keep the eyes closed and move them downward or place the fingers on the eyes in order to help to keep them closed. The procedure is very useful also for detecting any movements of the eyes through the fingers, allowing the technicians to take notes. Anyway, in order to detect ocular artifacts and distinguish them from possibly EEG's low waves, dedicated electrodes for recording the electrocardiogram are required and should be inserted into the montage. We can use different montages according to the availability of free channels on the amplifier. Typically, we use 4 electrodes in a bipolar montage, as you can see in the picture. The difference between channels E1 and E2 shows if the user is looking up or down. The difference between channels E3 and E4 depends if the user has looked to the left or to the right. In addition, we can use an alternative montage, as it's shown in the picture here. We can use only 2 channels, using the E1 electrode over the right eye and the E2 electrode below the left eye. Using a specific montage for recording the EEG signal, we can correlate possibly ocular artifacts in the EEG with the real ocular activity. Let's talk now about the cardiac activity and the artifacts generated by this activity. The heart produces 2 types of EEG artifacts, and they are due mainly to electrical and mechanical activities. Both types are tightly locked to cardiac contractions and most easily identified by their co-occurrence with complexes in the electrocardiogram channel. The electrical artifact actually is the ECG as recorded from head electrodes, but it may not appear as obvious ECG because of the distance from the heart and the suboptimal axis for visualizing ECG complex details. Overall, it's most prominent when the neck is short. Within the ECG artifact, the E wave and T wave are usually not evident, and it appears as poorly formed QRS complex. Mainly, we can distinguish 2 different types of cardiac artifacts: the ECG artifacts and the pulse artifacts. The ECG artifact is generated by the electrical activity of the heart that is reflected into the EEG activity. The pulse artifact is generated by the mechanical activity, and it arises from the circulatory pulse and may be also considered as a type of electrode artifact. Usually, the ECG activity is not present in the EEG recordings because the cardiac and the brain electric fields are equipotential, but in some patients, some ECG artifacts can occur during the recordings, showing repetitive peaks with the same frequency of the heart rate. These peaks correspond to QRS complex, as it's shown in the picture here, and they are recording from the temporal region, mainly from the left side, and by using transversal montage with wide interelectrode distances. The peak's frequency is constant in the same patient, and the ECG artifact may change amplitude throughout the respiratory cycle. For instance, performing the hyperventilation, because breathing changes the position of the heart and its electrical vector with respect to the head. Referential recordings, combining both ears as a reference, tend to show less ECG artifacts than referential recordings to one ear. Generally, in babies, the EEG recordings are free from ECG artifacts. But sometimes, especially during ambulatory sleep recordings, when the head of the baby is placed on the left arm of the mother, the ECG activity of the mother can be reflected into the EEG signal of the baby. Periodic waves of sinusoidal or triangular shape may be picked up by an electrode on or near the scalpel artery as the result of pulse waves producing slight change of electrical contact between the electrode and scalp with each contraction of the artery. It typically follows the ECG artifact's peak, by about 200 milliseconds. Pulse artifact occurs most commonly over the frontal and temporal regions and less commonly over the occipital regions. However, it may be present anywhere. For instance, here in the picture, we have an example of how the heart contraction is reflected into the EEG signal, and we can identify the pulse artifact in the T501 and the P301 channels in the red selection. Pulse artifacts can usually be identified by decreasing the cutoff frequency of the low-frequency filter and simultaneously recording the ECG. In contrast to most other artifacts, the ECG artifact usually cannot be eliminated by corrective actions during the recording, such as improving the contact or replacing the electrode. Occasionally, repositioning the head towards the left or right is helpful. For instance, when mothers hold her baby during the EEG recording and some ECG artifacts occur, only changing the position of the baby or using a pillow between the head and the heart, the ECG artifact can be reduced or removed. In addition, touching the electrode producing the artifact can help to identify it by both confirming the movement of the electrode with the pulse and altering the artifact's appearance on EEG as pressure is applied. Contrary to ECG artifacts, pulse artifacts can be eliminated by reapplication of the electrode at some distance from the pulsating artery. To reduce the probability of ECG artifacts, care should be taken to avoid placing referencing electrodes M1 and M2 on soft tissue. The technologist should place these electrodes slightly higher on the mastoid process, just above the ear on the bony portion. They also may be placed on the earlobes. If artifact remains, then the technologies may physically link together or double reference by software the two referencing electrodes. This can be accomplished by using a derivation that allows the M1 to be linked with M2. In the next few slides, we will discuss the main artifacts that arise for the muzzle activity. The electromyography activity due to the contraction of the muzzle in the scalp and face is generally present and recorded during the EEG recording. As you can see in the picture here, our face and scalp consist of many muscles and each of them can be a good source of EMG artifact. Sometimes the EMG activity prevents to record the EEG signal in a proper way and with high quality, so that we have to apply filter for rejection this specific artifact. Muzzle activity causes very short potentials, which usually occur, and it can be made up of single and irregular spikes or interferential patterns. Sometimes it's not easy to distinguish the muzzle activity from beta activity or epileptiform spikes. Muzzle artifacts from scalp and face muzzles occur mainly in the frontal and temporal regions, but may be recorded by electrodes nearly anywhere on the head. Repetitive movements such as chewing, blinking, or tremor may give rise to a combination of fast muzzle and slow movement artifacts, which may resemble cerebral discharge, especially if the combinations repeat with similar shape. Such rhythmical combinations may occur in tremor of Parkinson's disease, photomyogenic responses after the photic stimulations, and other non-epileptic myoclonic contractions. On the other hand, seizures often cause muzzle activity, so that a recording electrode picks up both cerebral seizure activity and the tonic or rhythmic muzzle activity cause the seizure. We can distinguish three main artifacts that arise from the muzzle activity: muzzle artifact, EMG artifact, and photomyogenic artifact. In this picture, in the Rectus square, we have a typical example of muzzle artifact. Sometimes it's not easy to distinguish the muzzle artifact from beta activity or epileptoform spikes. Reducing the settings of the high frequency filter will reduce the amplitude of these pulse potentials, but will also change their form so that single muzzle potentials may look more like abnormal epilepsy for spikes, and repetitive potentials may look like cerebral alpha or beta activity. In the picture here, we have an example of muzzle artifact with high amplitude and fast activity that occurs across bilateral anterior regions due to the facial muzzle contraction, and the distribution reflects the locations of the muzzle generating the artifact. Some recordings performed by using needle electrodes, also with coma patients, can be affected by muzzle artifacts which are generated by the reaction of the muzzle when the needle is inserted. Here we have an example of EMG artifact that mainly differs from the muzzle artifact because the potentials recur with nearly fixed interval and without significant change in waveform. In addition, this is typically limited in distribution to one electrode, T3 in this example, and in duration, which is briefer than epileptiform spikes. Repetitive EMG artifact may occur with a photic stimulation as a time-locked facial muzzle response to the flash of light. This is then a photomyogenic response and occurs over the frontal and the periorbital regions bilaterally. The photomyogenic response has a 50 millisecond latency from the flash and may occur synchronously with the occipital photic stimulation driving response. In this example, the artifact is generated by a 6 Hz photic stimulation, and the stimulations are transient across the frontal region that reflects an involuntary muzzle contractions. Generally, it may be present with eyes open or closed, but tends to occur more often with eyes closed. Muzzle artifact, even if not related to recognizable movement by the patient, is usually easily identified by its shape and repetition. It can be reduced and also eliminated by asking the patient to relax the jaw or open the mouth slightly or change position. Regarding the photomyogenic artifact, obviously it will disappear immediately as soon as the photic stimulation is stopped. Concerning the non-physiologic artifacts, in the next few slides we will discuss artifacts arising from recording electrodes, electrical interference, and the particular technical operations and procedures used in specific environments like in ICU. Most artifacts in this category are distinguished by one or more of the following characteristics: differ radically from previously recorded activity, they don't blend with other simultaneously recorded activity, they appear only in channels connected to one electrode, although some of these artifacts have characteristic shades. Others lack such features and may occasionally resemble cerebral activity. The main electrode artifacts are classified according to these events: Electrode Pop, lead movements, Electrodermal Activity, Salt Bridge Artifact. The common electrode artifact referred to as an electrode pop is due to a sudden change of electrode contact causing deflections in the EEG, which suddenly deviate from the baseline and gradually return. Sometimes it's not easy to identify this type of artifact, but its shape is very characteristic. As in the example in the picture that is shown with the red arrow, the electrode pop is caused by a sudden change in capacitance at the scalp electrode interface. Usually it can resemble the calibration signal. With the relays of the charge, there is a change in impedance and a sudden potential appears in all channels that include the electrode. In the example in the picture, the F3 channel is affected by the artifact. Occasionally, electrode pops resemble abnormal spike discharge. Movement of the head and body or of the electrode wires can cause artifacts even if all electrodes make good mechanical and electrical contact. Some movement artifacts can be identified by their rhythmical appearance, as for example tremor, chewing, sucking, or breathing movement artifacts. Leg movement has a more disorganized morphology that doesn't resemble true EEG activity in any form and often includes double phase reversal without the consistency in polarity. The picture here shows an example of lead movement, and in the red square we can see that many channels are affected by the artifact and involved in the movement. Respiratory artifacts are characterized by low activity, coming from the occipital region and synchronized with the respiratory events. Mainly, the respiratory events occur during the hyperventilation or when the patient is in the supine position with the head on the pillow. The low activity is generated by little change of the contact pressure between the electrode and the skin. The artifact is generally eliminated by asking the patient to change the position. Tremor artifacts are generated by tremor of the head or limbs, and the recorded activity is very similar to theta read. Patients suffering from Parkinson's disease generally show the tremor artifact in the posterior regions, and when the tremor is made localized on the hand, the artifact can be identified in the frontal regions. The electrodermal activity generates the perspiration artifact that arises from skin change and consists of low waveforms that are usually greater than 2 seconds in duration. As we can see in the example here in the picture, perspiration causes slow shifts and the electrical baseline by slowly changing the electrical contact between the electrode and the skin. In addition, sweat gland activity produces slowly changing electrical potentials that are recorded by the electrodes. Perspiration artifact almost always appears in more than one channel. For instance, in this example, we can identify the artifact as T3 and O1. Another typical artifact is defined as salt bridge artifact, and it's generated when the electrodes are too close to each other, and some excess of gel paste or red area can create a short circuit between the electrodes. The artifact is simply characterized by the presence of low amplitude EEG traces or isoelectric traces in the worst condition, as it's shown in the example in the picture at the derivation FP1 F3. A partial or complete loss of contact between the electrode and the scalp in the amplifier input results in an output reflecting only the difference between the remaining input with the intact electrode contact and the ground of the amplifier. If a ground electrode has been placed on the patient, then the output of the amplifier will reflect the potential difference between the patient ground and the electrode that still has good scalp contact. If the ground electrode has been placed near the eye, then eye movement artifact will appear in the channel of the amplifier. This is the reason why the ground electrodes should be placed at FPZ. Such recordings are referred to as ground recordings. The intrusion of eye movement into channels which ordinarily do not contain eye movement artifact, for instance the occipital derivations, alerts the technologist that one of the scalp electrodes has poor contact. Identification and correction of artifacts in the distribution of one electrode requires checking electrical and mechanical continuity. Because the artifact is often due to the faulty contact between the electrode and the scalp, the first step is to look at the junctions. The electrode may be partially or completely detached, and the lead wire may be broken, or the conductive base or jelly may have dried. So, as a next step, electrical impedance should be always measured because it represents a good marker for identifying some defective electrode. When the impedance value is too high, the EEG signal could be affected by alternating currents and interference, and so the EEG activity will be distorted and not visible anymore. The artifact can be removed if the electrode is refilled with a conductive jelly or paste, reapplied or replaced if it's defective. Many movement artifacts can be removed by simply asking the subject to stop moving. In persons who cannot comply, for instance in restless or confused patients, infants, patients with movement disorder, a technically adequate recording may not possible. In addition to carefully observing the patient and the recording and making frequent notations regarding movement, the technologist should identify and monitor movements by placing EEG electrodes or other sensors directly on the part of the body that's moving, for instance on the arms or legs for recording the muscle movement. Regarding the electrodermal activity, the perspiration artifact can be reduced by cooling the patient and drying the scalp with fan or alcohol. One of the most important types of artifact that affects the EEG recording is generated by electrical interferences. The artifact is due to the electrical interference generated by electrical equipment and nearby power lines. The most common external artifact is due to the alternating current present in the electrical power supply, and it has a frequency which can vary from country to country. For instance, we have 60 Hz in US and 50 Hz in Europe. Unfortunately, a slight amount of this interference is always present wherever alternating current is used. While electrical interference may be picked up by faulty electrodes and may appear in one or few channels, a huge amount of interference can cause artifacts, even with good recording electrodes and equipment. These artifacts are then likely to appear in all channels of all recordings made in the same recording form. The artifacts may be introduced either electrostatically by moving charged objects or electromagnetically by strong current flowing through cables and equipment such as transformers and electromotors. In this example, the artifact was generated by eliminating the 60 Hz notch filter, but it's a way to show you how the typical electrical interference generated by the power line appears into the EEG recording. The noise is usually medium to low amplitude and has the monomorphic frequency of the current, which is 60 Hz or 50 Hz. The artifact may be present in all channels or in isolated channels that include electrodes that have poorly matched impedances. The main solution to reduce the electrical interference generated by the power line is to apply the notch filter. Electrostatic and electromagnetic interference can be reduced by shielding the offending power cables, by using a shield room for the recording, and by proper wiring of the power cables. A good installation and proper setup of the system assures, in addition to the safety of the patient, A good rejection of electrical interferences by powering all the systems parts using a medical grade power supply for the amplifier, and an isolation transformer for the acquisition PC and any other external parts, for instance printer, monitor, if they are placed in the patient care area and quite close to the amplifier. Last but not least, the impedances have to be checked at the beginning of the EEG recording and more times during long-term monitoring, by reaching impedances as much lower as possible and similar each other, in order to avoid that the alternating current or any electrical interference can rise into the EEG recording. The external devices represent the last big family of sources that generate introduced artifacts into the EEG recordings. Let's see in the next slide what are the main sources and how the artifacts appear in the EEG and how we can reduce them. Sometimes in some special and critical environments like ICU and OR, specific operation and the patient are required in order to evaluate better the clinical conditions, and so some external medical devices like ventilators, multi-parameters monitors can be installed close to the EEG system and used in order to assure the maintenance of the vital signs. For such reasons, it's so common to generate artifacts when the medical staff accidentally touch or push the electrodes and the wires, or when some external medical device is connected to the patient during the monitoring and produces and introduces some noise or artifacts into the EEG recording. Unfortunately, any device with an electric motor may produce high amplitude, irregular polyspike-like or spike-like artifacts. Typically, the artifact occurs with the motor's activity, and so it may be constant or intermittent. For instance, the infusion pumps generally represent a typical sources of artifacts in ICU. The main external device that may generate artifacts during EEG recordings are electrical motors, mechanical ventilator, and circulatory pump. Here we have an example of artifacts generated by an electrical motor. In fact, the very high frequency activity suggests an electrical source, and the fixed morphology and repetition rate indicate an external device. Mechanical devices such as ventilators and circulatory pumps usually produce artifacts with slower components than other electrical devices. The artifact typically repeats with a fixed interval and is a slow wave as it's shown in the picture with the red square, or a complex including a mixture of frequencies superimposed on a slow wave. In this example, we can easily recognize the sharpest repetitions in the frontal regions, mainly at FP1 and FP2 channels. In addition, the A2T4 derivation is affected by the typical pulse artifact because it's synchronized with the QRS complex of the ECG signal that is recorded in the EKG channel. So, the artifact in this example is due to a circulatory pump providing circulatory support and extracorporeal oxygenation. In order to avoid that some noise and artifacts can arise from some active part of any external device or from their operation, we should keep all the noise sources as far as possible from the recording part of the EEG system. For instance, in ICU, the technicians should place the EEG Amplifier and the EEG electrodes as far as possible from the other medical devices. In the worst condition, for instance in OR, if we are not able to reduce the noise and the artifact, we should switch off the external devices that are not required during the recording, for instance the optical microscope. Last but not least, for the same reason of the first point, the technicians always must sure that the electric wires should be placed far from the noise sources. In the last part of this webinar, we will discuss the methods and the suggestions for reducing or eliminating the EEG artifacts. said, and as we saw in the first part of this presentation, artifacts are undesired signals that may introduce changes in the measurements and affect the signal of interest. Even if the ideal way of working with EEG signal is to avoid the occurrence of artifacts while recording, the EEG signal is unfortunately often contaminated by various physiological and non-physiological factors other than cerebral activity, which are typically of non-interest. For instance, cardiac activity, ocular movements, eye blinks, and muscular activity are among the most common types of artifacts. Due to the sources of noise being very diverse and having different characteristics, most researchers focus on removing single types of artifacts. The cancellation of noise and artifacts is an important issue in EEG signal processing and normally a prerequisite for the subsequent signal analysis to be more reliable. For clinical applications, raw signals may still suffice to separate groups of good and bad prognosis, but other applications IMED research requires data as artifact-free as possible. During the last years, only a few novel methods have been proposed in the artifact removal area, in addition to classic existing approaches such as regression, ocular artifact correction, filtering, or the more widely used blind source separation techniques. Anyway, the sample, slow pass, band pass, or high-pass filtering and artifact prevention still represent the first classical attempts at removing artifacts from the measured EEG. Artifact removal techniques surely represent an important aspect, and maybe they could be the new frontier in the quality of the EEG recordings. However, the signal processing is using information coming from a recorded signal, so firstly we should mainly focus on the quality of the EEG recorder. In this case, the EEG Amplifier and has a next step take into consideration other parts belonging to the EEG systems like the EEG supplies, because all these parts as well as the patient preparation play an important role into the quality of the EEG recordings. Concerning the EEG Amplifier, we mainly should consider three important parameters: the common mode reaction ratio, the input noise, and the input impedance. The common mode reaction ratio allows to reject in phase and amplify out of phase potential. For instance, the power line noise is a signal which typically affects all the parts of the body and the EEG system in the same way. So each electrode introduces a noise signal with similar voltage and the same phase. Since the differential amplifier rejects the signals in phase, the power line noise will be rejected. The input noise consists mainly from the noise caused by the analog amplifier and by AD converter. So, for instance, it depends on the low pass filter, the sample rate, and the choice of electronic circuit, and it should be as low as possible. The modern EEG amplifiers have a high impedance to verify that the connection between the electrodes and the scalp is negligible and warm as if the electrode doesn't have any contact at all. Higher is the input impedance of the amplifier and more negligible will be the impedance values between electrodes and scalp, and for this reason much more similar to each other. Typically the input impedance is 100 megaohm, but EEG amplifier with input impedance too much high, for instance greater than 1 gigaohm, could prevent to record properly the EEG signal and display a low quality EEG signal. The patient preparation is a very important part in the methodology EEG, and it should be properly performed before to start a new EEG recording. Here we have all the steps for your review and reference. First of all, we have to start to clean properly the skin surface by using a cotton swab, preferably with a flexible stick, in order to apply the skin preparing products. Typically, we use a mild abrasive gel. Then, we will have to choose proper electrodes according to the patient and the clinical application. For instance, the consideration of disposable electrodes should be evaluated for use on the critical ill patients. In addition, we can choose from different types, material, and size of electrodes. For instance, we can use gold, silver chloride electrodes for adults or for infants. Typically, gold and silver chloride are the most used and required, mainly for LTM and sleep recordings. Often in ICU, the needles electrodes are required and used with coma patients and for the assessment of the brain death. For infants, sometimes adhesive electrodes are preferred. Next step is to fill the head of the electrode with a conductive medium that represents the electrode, and personally I suggest to use a large amount of conductive medium. Finally, cover the electrode to secure and check the impedances. The American Clinical Neurophysiology Society guidelines recommend that impedances should be less than 5 kΩ. Unfortunately, this procedure is not always performed in a proper way, and nowadays, considering the high level of the technology achieved, it represents the main cause of degeneration and the introduction of noise and artifacts into the EEG. For sure, another important aspect that plays a fundamental role in the quality of the EEG recordings is represented by the EEG supplies. The abrasive gel is used for cleaning the skin in order to reach low values of impedances between skin and electrodes. It improves conductivity and achieves maximum efficiency with the equipment, and so for this reason it is very important to use a gel which doesn't leave any contaminants after the cleaning, because they could alter the contact between electrodes and skin and increase the impedance values and compromise the stability of the contact. The conducting and adhesive base is a specific electrolyte with specific characteristics designed for allowing to fix the electrodes on the skin and transmit the EEG signal. The paste has two main characteristics. The first is the ability to hold the electrodes fixed to the skin as long time as possible without lose the ability to gather and transfer the EEG signal from the scalp to the EEG amplifier. So, the good conductivity represents the second important characteristic of the electrolyte. EEG electrodes are the first instrumental link between the electrical generators in the brain and the EEG record itself. EEG electrodes are pieces of metal held against the scalp with a conductive jelly, the electrolyte, and with wires connecting them to the inputs of the EEG amplifier. When metal is placed in contact with an electrolyte, a voltage develops between the metal and the electrolyte due to the formation of a layer of electrical charge on the surface of the electrode. Different metals generate different voltages with the same electrolyte. Chlorided silver and gold disc electrodes have the best properties of all materials, having little drift and a long time constant. Because of these differences between electrode materials, it is important that all electrodes placed on the scalp of the patient be of the same material. Natus Medical is a global market leader, bringing together leading technology from Dantec, Grass, and Blaniconix Tech. Thanks to the great experience that Natus has gained in the last years and the know-how belonging to each company, now Natus has the opportunity to provide the best solutions also for the supplies. The EEG supplies are the result of an important and accurate analysis of the customer's needs and the different applications, selecting and providing the products with the highest quality in order to satisfy all the requirements in the market. In addition, the EEG supplies and Natus acquisition systems are manufactured and tested together, and this is an important advantage for the end users because Natus can suggest in advance the best setup and provide the best solution according to the clinical applications in order to assure EEG recordings with the highest quality possible and with the lowest level of noise. With reference to the previous slides where we discussed the patient preparation and the EEG electrodes, here we show some of the main EEG supplies, like the abrasive gel, the conductive base, and the EEG electrodes that you can find in the Natus Global catalog and that you can purchase directly from Natus. For your convenience, Natus has already created for your sample for you some supplies, starter kits with all the required supplies according to the specific modality. For instance, for the EEG, ICU, RTM, and sleep modality. We are able to use all these kits with all the Natus EEG systems and with other EEG systems in the market. For your reference, here in the table you can find the part numbers related to the supplies starter kit and a global catalog that you can download directly from the Natus website. So, the presentation is over and I would like to thank you for your time and for your attention. The recorded session of this webinar will be made available on NTA website, and for any further questions please email me to my email address francesco.mucci@natus.com.